So, homework number 6 on chapter 7 is due on the 22nd. We're going to keep going on chapter 7. So, let's look at work done by a constant force. The work done by a constant force, if the force is at an angle to the displacement, work equals force times distance times the cosine of the angle. Work is the dot product of the force vector and the distance vector, the displacement vector. But that's just force times distance times cosine of the angle between them. That's like definition of the dot product from the magnitudes. There's another way to calculate dot product. So if you know that, that might be relevant in some rare problems, but this is just same thing. And the work energy theorem is that the total work is change in kinetic energy. So that's 1/2 mv final squared minus 1/2 mv initial squared. Dominica. So if you lift a 4.1 kilogram box vertically from rest over a distance of 1.6 meters with a constant upward applied force of 52.7 newtons, we want to find the work done by the applied force, the work done by gravity, and the final speed of the box. So I'll give you guys a couple of minutes to work on it.
Did you finish reading the exams?
Yes, I finished grading the exams. I'm not handing them back today because I have someone making it up right now.
Okay.
So I want to have him to grade his, but your grades are up on Blackboard. So you can check them if you want. And if you want to, after class, look at them, I'm happy to show you.
Okay.
It's just because I need them to finish grading and I need to get that grading done. Like, I'll be handing them back on Wednesday. I just need them. Sometimes you need to compare to other people's stuff to grade right, and so for partial credit. That's why I haven't handed it back. But they are graded. I'm happy to show them to you after class. So for this, mass is 4.1 kilograms. Distance is 1.6 meters. Force is 52.7 newtons. Initial velocity is 0 meters per second. So work from the applied force, we want to find work from the applied force, work from gravity, and the final speed of the box. The work from the applied force is going to be force times distance times the cosine of 0. So 52.7 newtons times 1.6 meters times 1, which is 84.3 joules. The work done by gravity is going to be mass times g times distance, the weight times the distance times the cosine of 180 degrees. Because gravity is opposite the direction the box is moving. So 4.1 kilograms times 9.81 meters per second squared times 1.6 meters times -1, which comes out to minus 64.4 joules. And to figure out the final speed, well, the total work is just the sum of the applied work plus the gravity. So 84.3 joules minus 64.4 joules, which is 19.9 joules. That is also equal to the change in kinetic energy. 1/2 mass times velocity final plus 1/2 mass times velocity initial. Our initial velocity is 0. So that's just equal to 1/2 mass times velocity final. So final velocity is 2 times the total work over the mass. 2 times 19.9 joules over 4.1 kilograms gives us a final velocity of 3.12 meters per second. So when a father takes his daughter out for a spin in a stroller, he exerts a force F with a magnitude of 44 newtons at an angle of 32 degrees below the horizontal, as shown in the sketch. The stroller and the child together have a mass of 22.7 kilograms. How much work does the father do on the stroller when he pushes it through a horizontal distance of 1.13 meters? So the angle between the displacement and the force is 32 degrees. If the initial speed of the stroller is 1.37 meters per second, what is the final speed? Assume the stroller rolls with negligible friction. The only force involved, the only work is the work done by the father. Because all these other forces involved, the weight, the normal forces are all perpendicular to the displacement, so they do 0 work. So here, we know our force is 44 newtons. We know our angle is 32 degrees. Our mass is 22.7 kilograms, and the distance is 1.13 meters. First, we want to find the work done. Then we know the initial velocity is 1.37 meters per second, and we want to find the final velocity. So let's start. Work is force times distance times cosine of angle. The 44 newtons times 1.3 meters times the cosine of 32 degrees. That's just 42.2 joules. The work is fairly straightforward. Work is also equal to change in kinetic energy. So that's 1/2 mass times velocity final minus 1/2 mass times velocity initial. We're looking for velocity final. So we can do a little bit of algebra. 1/2 mass times velocity final is 1/2 mass times velocity initial. Oh, sorry. Mass times velocity final squared and mass times velocity initial squared. 1/2 mass times velocity final squared is 1/2 mass times velocity initial squared plus the work. We can divide everything by 1/2 mass and get velocity final squared is velocity initial squared plus 2 work over mass. And then we can take the square root. And apparently something got jiggled out of order. Velocity final is velocity square root of velocity initial squared plus 2 times work over mass. So that's 1.37 meters per second quantity squared times plus 2 times 42.2 joules over 22.7 kilograms, all square rooted. And that comes out to 2.37 meters per second. And while I'm thinking about that, let me quickly fix the animation order. That's not what I wanted to do. That is. So, you have a car. To accelerate a certain car from rest with some speed v requires work W1, as shown down here. The work needed to accelerate the car from v to 2v is some work W2. Which of the following statements is correct? Work 2 equals work 1, work 2 equals twice work 1, work 2 equals 3 times work 1, or work 2 equals 4 times work 1. And which of these is the best explanation? 1, the increase in speed is the same, so the work is also the same. 2, to double the speed requires double the work. 3, kinetic energy depends on v squared, and hence it takes 4 times as much work to increase the speed to 2v. Or 4 times as much work is required to go from 0 to 2v as to go from 0 to v. Therefore, the work required to go increase the speed from v to 2v is 3 times the original work. So I'll do a quick poll. I guess I can see what people online have as opinions. You can use reactions or what you want to put your hand up for. So who thinks it's option 1 here? To increase the speed, the increase in speed is the same, so the work is also the same. No one? Okay. Who thinks it's option 2? To double the speed requires double the work. No one? Option 3, kinetic energy depends on v squared, and hence it takes 4 times as much work to increase the speed to 2v. Or four times as much work is required to go from 0 to 2v as to go from 0 to v. Therefore, the work required to increase the speed from v to 2v is 3 times the original work. Well, all of you who said yes on this were correct. It is 3 times the original work, because it takes work 1 to go from 0 to v, 4 times work 1 to go from 0 to 2v, with the difference 3 is the work required. So we've been dealing with a constant force. We can also interpret this as when you're dealing with a variable force. So if the force is constant, we can interpret the work done graphically as, force times distance over work. But if the force varies, work is equal to the integral of force dot dx. That's sort of a more general thing with, I guess it would end up being, because it's dot product, would be like force cosine theta dx, but we're not going to worry about the cosine theta. We're just going to deal with force in the same direction as, or more or less the same direction as position. There won't be a cosine theta in there. It would actually be something like integral of force as a vector dot dx as a vector, but no one wants to do that, so you get calculus. We're going to deal with the case where essentially cosine theta is 1. Where force and position are more or less in the same direction. They can be in the same direction or they can be opposite. So force can be a negative number. So we can interpret the work done graphically like this. And if the force takes on several successive constant values, we can add them up, because it's basically an integral. You can do it piecewise. And then you can approximate a continually varying force by a succession of constant values. So again, work is just the integral of force dx. If force is a function of position, then work is force integrated over x. So work is the integral from the initial position to the final position of force dot dx. If force is constant, you get the integral from initial position to final position of force times cosine theta dx. And we're interested in the situation where cosine theta equals 1, basically. So the force needed to stretch a spring an amount x is force equals kx. So the work done stretching a string. So this is the work. This is the force applied to the spring, not the work done by the spring. Is 1/2 kx squared. The work done by the spring is minus 1/2 kx squared. So the work is the integral from 0 to x of kx dx. So it's 1/2 kx squared. So the work done in stretching the string ends up being 1/2 kx squared. And you can also do it graphically like this. And if you go the other way, you have a negative x and a negative force. They cancel out. You still get 1/2 kx squared. Oh. So for a spring, the work to stretch a spring, work on spring is 1/2 x squared. The work by the spring is minus 1/2 kx squared. So a toy snake has a spring with a force constant of 230 newtons per meter. How much work is required to stretch this spring 2.5 centimeters? And the spring in a car suspension has a force constant of 21,000 newtons per meter. If 3.5 joules of work is done, how far is the spring compressed? So here, for our first problem, K is 230 newtons per meter. X is 2.5 centimeters. We want to find the work to stretch this spring. So work is 1/2 kx squared. We will have to convert x to meters, so that will be 1/2 times 230 newton newtons per meter times 0.025 meters quantity squared, which comes out to 0.072 joules. And just to stay in convention with the previous slide, stretch here is positive. So for compression, that will be negative. So for B, K is 21,000 newtons per meter. Work is 3.5 joules. And we want to figure out how far the spring is compressed. We're looking for X. So work is 1/2 kx squared. X squared is 2 times work over K. So X is square root of 2 times work over K. So X is equal to 2 times 3.5 joules over 21,000 newtons per meter, which is 0.018 meters or 1.8 centimeters. Though I should have put a minus sign on those because it was compressed instead of stretched. But basically, there's two possible answers to this. One is positive, one is negative, one is stretched, one is compressed. They're the same value though. So same distance. Yeah. Let me do plus minus minus. I'll re-upload these slides. So the work required to deflect a typical AFM, which stands for atomic force microscopy, cantilever by 0.1 nanometers is 1.2 times 10 to the minus 20 joules. AFM is actually pretty cool. It lets you image really at the scale of atoms with a surprisingly simple design. You basically run a needle over the surface. You just have to make a really sharp point. What is the first constant of the cantilever, treating it as an ideal spring? And how much work is required to increase the deflection of the cantilever from 0.1 nanometers to 0.2 nanometers? So yeah. So for this, we know our x1 is 0.1 nanometers, which is 1 times 10 to the minus 10 meters. We know work 1 is 1.2 times 10 to the minus 20 joules. We want to find K. Also for part B, x2 is 0.2 nanometers, or 2 times 10 to the minus 10 meters. And we want to find the change in work from 0.1 nanometers to 0.2 nanometers. So for that, we're going to need to find work 2 and subtract it from work 1. Work 1 is 1/2 kx1 squared. So k is 2 times work 1 over x1 squared. So 2 times 1.2 times 10 to the minus 20 joules over 1 times 10 to the minus 10 squared. That 10 to the minus 20 cancels the 10 to the minus 20. K is 2.4 newtons per meter. This is actually a pretty easy bit of math. Well, now that we know that, work 2 is going to be 1/2 kx2 squared. So that's 1/2 times 2.4 newtons per meter times 2 times 10 to the minus 10 meters squared, which will end up 4 times work 1 at 4.8 times 10 to the minus 20 joules. And if we're looking at the change in work, that's work 2 minus work 1. So 4.8 times 10 to the minus 20 joules minus 1.2 times 10 to the minus 20 joules gives us 3.6 times 10 to the minus 20 joules. Any questions? So here we have a block with a mass of 1.5 kilograms and an initial speed of 2.2 meters per second, and it slides on a frictionless horizontal surface. The block comes into contact with a spring that's in its equilibrium position and compresses it until the block comes to rest momentarily. Find the maximum compression of the spring, assuming the force constant is 475 newtons per meter. So here, you're going to use the fact that here you use the work done by the spring is going to be minus the work on the spring. So work done by the spring is minus 1/2 kx squared. And that is going to equal the change in kinetic energy of the block. So we start with some initial velocity, we end with 0 velocity, and we've compressed the spring. So our initial velocity is 2.2 meters per second, our final velocity is 0 meters per second. Our mass is 1.5 kilograms. Our spring constant is 475 newtons per meter. We want to find out what X is. So we need to know the work done by the spring, the work done by the block, the kinetic energy initial, the kinetic energy final. The initial kinetic energy is a 1/2 mass times velocity initial. So 1/2 times 1.5 kilograms times 2.2 meters per second squared, so 3.6 joules. Final kinetic energy is 0. So the work done to the block, sorry, this is the work done on the spring, the work done on the block. The work done on the block is changing kinetic energy, so final kinetic energy minus initial kinetic energy. That's 0 joules minus 3.6 joules. That's minus 3.6 joules. But the work done by the block is done on the block is done by the spring, so it is minus the work done by the spring. Sorry, minus the work done on the spring. Blah, 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 blah. Minus the work done on the spring. So the work done on the block is minus 1/2 kx squared. That's the work done by the spring. This is work by spring. The work done by an object is equal to minus the work done on that object. It's always the case. So if we solve for x, it will be minus 2 work done on the block over k. So minus 2 times minus 3.6 joules over 475 newtons per meter square root, which gives us an x of plus or minus 0.12 meter, or 0.12 meters is what we're interested in. That's how much the spring compresses. I guess that would be positive in this case. So we talked about work. Well, we can also talk about the derivative of work. Power is the derivative of work, the time derivative of work. So power is the work dt, so generally it is work over time. So generally power is work over time. So it's a measure of the rate at which work is done. The power is work over time. The SI unit is the joule per second, which is the watt, named after James Watt, who vastly improved the steam engine and sold it quite effectively, and also invented another common unit of power, the horsepower. So the SI unit of power is the watt. A commonly used unit of power is the horsepower. 1 horsepower is 746 watts. That's because 1 horsepower is defined to be 550 foot-pounds per second. Yeah, foot-pounds per second in the US customary units. But the unit of power in US customary units is foot-pounds per second. So horsepower gets used a lot more often. Horsepower is 746 watts. This is a unit that James Watt invented to sell steam engines, so it does not correspond in any nice direct way to the power output of a horse. It's some sort of average power output of a horse over a day of work. Yeah. So horses can output more than 1 horsepower. So some typical values of power. Hoover Dam has an approximate power of 1.34 times 10 to the 9 watts. Or 1.34 gigawatts. Giga? Yes, gigawatts. A car moving at 40 miles per hour has a power of 7 times 10 to the 4 watts. A home requires a power of 7 times 10 to the 4 watts. A home stove has a power of about 1.2 times 10 to the 4 watts. 12,000 watts. Sunlight falling on 1 square meter of land has a power of 1380 watts. There's some things having to do with angles there, but sunlight falling on 1 square meter is 1380. A refrigerator has a power of 615 watts. Television is about 200 watts. A person walking up the stairs is using about 150 watts. A human brain uses about 20 watts, about tons more. But it is always doing that. So here, to pass a slow moving truck, you want your fancy 1.3 times 10 to the 3rd kilogram, so 1,300 kilogram car, to accelerate from 13.4 meters per second, 30 miles per hour, to 17.9 meters per second, 40 miles per hour, in a time of 3 seconds. What is the minimum power required for this pass? So remember, power is work over time. So you can work out the change in work with the work energy formula and divide it by the time required to find the power. So, minimum power required for this pass? Well, our initial velocity is 13.4 meters per second. Our final velocity is 17.9 meters per second. Our mass is 1.3 times 10 to the third kilograms. The time required is 3 seconds. We're looking for the power. To find the power, we're going to need to know what the work is. Because power is work over time. We know time, but we need work. So work is change in kinetic energy. That's 1/2 mv final squared minus 1/2 mv initial squared. So that's 1/2 times 1.3 times 10 to the third kilograms times 17.9 meters per second squared minus 1/2 times 1.3 times 10 to the third kilograms times 13.4 meters per second squared, which comes out to 9.16 times 10 to the 4 joules. Power is going to be work over time. So 9.16 times 10 to the 4 joules divided by 3 seconds gives us 3.05 times 10 to the 4 watts, or if you convert it, 40.9 horsepower. And in an actual situation like this, you would require more power because this is ignoring all the power required to overcome air resistance and things like that. Yeah, this is what would happen if you had no friction. Now, if object is moving at constant speed in the face of some resistance, friction, gravity, air resistance, whatever. Well, if you're moving at constant speed, work is just going to be force times distance. Power is force times distance over time. So force times distance over time, that's force times velocity. So if you're moving at constant speed, your power is just going to be the force required times your speed. In the face of some resistive force. So here, if it takes a force of 14,050 newtons to keep a 1,300 kilogram car, thank you, moving with a constant speed of a slope of 5.25 degrees. If the engine delivers 4.10 times 10 to the 4 watts, 55 horsepower to the wheels, what is the maximum speed of the car? So we know what the force is, and we want to find what the speed required is for this power. So in this case, because we're dealing with working against gravity, the force is independent of speed. So what's the maximum speed we can achieve? So power is force times distance over time, so it's force times velocity. You're working against some it's for constant speed. So force is 1450 newtons. The angle up the slope is 5.25 degrees. The mass of the car is 1,300 kilograms. The power required is 4.1 times 10 to the 4 watts. The velocity is unknown. So it turns out we don't need the angle, we don't need the mass, because the force is in the same direction of the motion. Basically that 1,300 kilograms and 5.25 degrees is what generates the force. So power is force times velocity. The velocity is going to be power over force. The velocity is 4.1 times 10 to the 4 watts divided by 1450 newtons, which gives you a velocity of 28.3 meters per second, which is quite a clip. But then 5.25 degrees is not the steepest slope. So that is the end of chapter 7. So if the force is constant and parallel to displacement, work is just force times distance. If the force is not parallel to displacement, work is force times cosine of the angle times distance, so force times distance times cosine of angle. The total work, you add up the work from every force, that equals the net force, the total force times the cosine of the angle times distance. The SI unit of work is the joule. So again, this is the angle for the net force. So it's often, sometimes it's easier to find the total force and use that to work out the total work. Sometimes it's easier to deal with the individual forces because some of them will just fall out, go away. Depends on the situation. The SI unit of work is the joule. Total work done on an object or a thing is equal to its change in kinetic energy. So change in kinetic energy is 1/2 mass times velocity final squared minus 1/2 mass times velocity initial squared. Kinetic energy is defined as 1/2 mass times velocity squared. Work done against a spring force is 1/2 kx squared. This is not the work done by the spring, this is the work done against the spring. The work done the work you do to compress the spring or stretch it. It's also the energy you have stored in the spring as potential energy, but we'll get to that in the next chapter. Power is the rate at which work is done. It's work over time. The SI unit of power is the watt. There is also the horsepower, which is 746 watts. Any questions? Since we only have like 10 minutes left, I don't really feel like starting chapter 8. There's also a lot of people not here today. So I'll just start that up on Wednesday. I'll see you guys on Wednesday. If you want to look at your test quickly, you can. But I need, oops.